Tonight, if sleep feels distant, let us gently explore one of the most famous thought experiments in quantum physics. It is known as Schrödinger's cat. You do not need to solve anything. You do not need to understand every equation. Just listen slowly. Allow the idea to unfold softly in your mind. Imagine a sealed box. Inside that box is a cat. Also inside the box is a tiny radioactive atom, a Geiger counter, and a small vial of poison. The setup is simple. If the atom decays, the Geiger counter detects it. If the Geiger counter detects decay, it breaks the vial. If the vial breaks, the poison is released. And if the poison is released, the cat dies. If the atom does not decay, the cat remains alive. The entire system depends on a single quantum event, the decay of one tiny atom. In quantum mechanics, before measurement, the atom exists in a superposition. It has both decayed and not decayed, not because we are ignorant, but because its state is genuinely described by a probability wave. Now imagine that the cat's fate is directly linked to that quantum uncertainty. If the atom is in superposition, then the entire system must also be in superposition, which means the cat is both alive and dead at the same time, not one or the other, but both possibilities existing together. This is the strange conclusion that Schrödinger wanted to highlight. He did not propose this experiment because he believed cats could truly be alive and dead. He proposed it to show how strange quantum mechanics appears when applied to everyday objects. At the microscopic scale, superposition is normal. Particles can exist in multiple states at once, but when extended to a cat, the idea feels absurd, and that absurdity forces us to ask a deeper question. When does superposition end? When does possibility collapse into a single reality? Let that question rest gently in your thoughts. A closed box, a quiet cat, a tiny atom undecided, alive, dead, or something more subtle. We will explore this slowly. Let us slow down even further. To understand why Schrödinger imagined placing a cat inside a sealed box, we must gently return to the subtle world of quantum mechanics. In everyday life, our reality feels firm and definite. A door is open or closed. A light is on or off. If we hide a coin beneath our hand, we assume it already shows heads or tails, even before we look. Classical physics supports this way of thinking. Objects possess definite properties at all times. Position, speed, energy, all precisely defined. But when scientists began studying atoms, this certainty began to soften. At very small scales, particles do not behave like tiny solid marbles. Instead, they are described by something called a wave function. The wave function does not tell us exactly where a particle is. It describes a range of possibilities. It assigns probabilities to different outcomes. And until a measurement occurs, the system does not settle into one definite state. It exists in superposition. Superposition means that multiple possibilities coexist, not because we lack knowledge, but because the mathematics describing the system contains overlapping states. Imagine a faint mist drifting through still air. The mist does not occupy one sharp boundary. It spreads gently across space. In a similar way, a quantum particle spreads across possible outcomes. An electron can exist in multiple energy levels at once. A photon can pass through two slits and create interference with itself. Experiments confirm this repeatedly. Interference patterns appear only if the particle behaves as a superposition of paths. So, superposition is not poetic language. It is a measurable feature of nature. Now return to the sealed box. Inside is a radioactive atom. Radioactive decay is unpredictable at the level of a single atom. We can calculate the probability of decay over time, but we cannot say exactly when one specific atom will decay. Before we check, the atom is described by a superposition of decayed and not decayed. Both possibilities exist in the mathematical description. Now connect that tiny uncertainty to something larger. If the atom decays, a detector is triggered. If the detector is triggered, a mechanism breaks a vial of poison. If the poison is released, the cat dies. If the atom does not decay, nothing happens. The cat lives. Each step depends entirely on the quantum event. So if the atom remains in superposition, then the detector must also be described as triggered and not triggered. The mechanism must be both activated and inactive. The vial must be both broken and intact. And the cat, entangled with this entire chain of events, must be described as alive and dead at the same time. Pause gently with that image. This is not meant to shock. It is meant to follow the logic carefully. Quantum mechanics does not contain a clause that says superposition applies only to tiny particles. The equations apply universally. If the microscopic system is indefinite, then the macroscopic system linked to it must also be described by the same mathematics. Alive and dead, contained within one wave function. Yet our experience tells us something different. When we open a box, we never see overlapping cats. We see one outcome: the cat is alive, or the cat is dead. So where does the superposition end? Does it stop at the atom, at the detector, at the boundary of the box, or at the moment a human observer looks inside? Schrödinger proposed this thought experiment to highlight this tension. He did not believe that cats exist in ghostly dual states. He wanted to show that if quantum rules are taken seriously, they lead to conclusions that challenge our intuition. The cat becomes a bridge between two worlds: the microscopic world of probability and the macroscopic world of apparent certainty. Inside the box, the system evolves according to quantum laws. Outside, the world waits in classical clarity. Somewhere between those domains, something changes. When we open the box, the wave function appears to collapse. One possibility becomes real, the other is no longer observed. But the theory itself does not clearly explain why this collapse occurs. It predicts probabilities. It calculates outcomes. Yet the transition from possibility to reality remains mysterious. Let that mystery rest softly in your mind. A quiet box, a silent room, a fragile atom suspended in probability, a cat described by overlapping states, alive, dead, or something even subtler than those simple words can capture. There is no need to resolve the paradox tonight. Just allow it to hover gently, like a wave that has not yet chosen where to settle. Let us continue slowly. We now approach the heart of the paradox. If the mathematics allows the cat to exist in a superposition of alive and dead, why do we never experience such a state? Why does reality appear definite the moment we look? This question leads to what physicists call the measurement problem. In quantum mechanics, the wave function evolves smoothly over time according to a precise mathematical rule known as the Schrödinger equation. This evolution is continuous, predictable, elegant. If a system remains perfectly isolated, its superposition remains intact. Possibilities overlap without conflict. But when a measurement occurs, something different seems to happen. The wave function appears to collapse. Instead of multiple overlapping possibilities, we observe one outcome: alive or dead. The smooth mathematical evolution gives way to a sudden jump. This jump is not described by the same continuous equation. It is introduced as a separate rule. And that separation creates tension in the theory. What exactly counts as a measurement? Is it the Geiger counter detecting radiation? Is it the poison interacting with the air? Is it the cat's body responding biologically? Or does collapse occur only when a conscious observer opens the box? Different interpretations offer different answers. The Copenhagen interpretation suggests that the wave function represents our knowledge of the system. When we measure, we update that knowledge. The collapse reflects a transition from potential information to actual information. In this view, measurement is fundamental. The act of interaction defines reality. But what qualifies as interaction? Does a detector qualify? Or must there be awareness? Most modern physicists believe consciousness is not required. A measuring device interacting with the system is enough. Yet even this leaves ambiguity. If a detector measures the atom inside the sealed box, does the wave function collapse at that moment? If so, then by the time we open the box, the cat's fate is already decided. But if the detector itself is treated as part of the quantum system, then it too should enter superposition. Triggered and not triggered, the chain extends: atom, detector, poison, cat, box, air molecules, room, observer. Where does it end? One modern approach to this puzzle is decoherence. Decoherence suggests that when a quantum system interacts with its environment, the delicate phase relationships between superposed states become scrambled. The system becomes entangled with countless surrounding particles. Photons scatter, air molecules collide, vibrations spread. Through this process, the interference between possibilities becomes effectively impossible to observe. The superposition does not vanish in principle, but in practice, it becomes inaccessible. The system behaves as if it has collapsed. In the case of the cat, even inside a sealed box, complete isolation is nearly impossible. Thermal radiation interacts with the environment. Microscopic vibrations connect the system to the outside world. These interactions rapidly destroy observable coherence. So when we open the box, we find one definite outcome. Not because superposition never existed, but because coherence has dissipated. Another interpretation takes a more radical stance. The many worlds interpretation proposes that the wave function never collapses at all. Instead, every possible outcome continues to exist. When the atom decays, reality branches. In one branch, the cat is alive. In another branch, the cat is dead. Both branches are equally real. They simply no longer interact. Opening the box does not eliminate possibilities. It places the observer into one branch. The other branch continues independently. This interpretation removes the need for collapse entirely. The mathematics remains continuous, unbroken, but it introduces a vast and almost unimaginable picture of reality. Countless branching histories, endless parallel outcomes. There are other ideas as well. Objective collapse theories suggest that superposition becomes unstable beyond a certain scale. Hidden variable theories suggest deeply deterministic layers beneath quantum randomness. Each interpretation attempts to answer the same quiet question: how does possibility become experience? Schrödinger's cat does not provide the answer. It provides the tension. It invites us to sit with uncertainty, to accept that the boundary between quantum and classical may not be sharp, And perhaps that is part of its beauty. A simple box, a silent cat, and a question that echoes through modern physics. When does the wave become real? There is no need to decide tonight. Just let the question rest. Softly, like a possibility that has not yet collapsed. Let us go a little deeper. We've seen that Schrödinger's cat reveals a tension in quantum mechanics. The mathematics allows superposition to extend from atoms to detectors, from detectors to cats. Yet experience presents us with a single outcome, alive or dead. Different interpretations attempt to explain this tension in different ways. Each one offers a lens through which we can view the same equations. The Copenhagen interpretation suggests that quantum mechanics is not a direct description of reality itself, but a tool for predicting measurement outcomes. In this view, the wave function represents our knowledge. Before measurement, we describe possibilities. After measurement, we update our description. Reality becomes definite when information becomes definite. This interpretation emphasizes practicality. It avoids metaphysical claims. It says, in essence, that quantum mechanics works, and that may be enough. But for some, this feels incomplete. It leaves open the question of what reality is doing when we are not looking. The many worlds interpretation takes a very different approach. It accepts the wave function as a real, physical object. It does not collapse. It evolves smoothly at all times. When a quantum event occurs, the universe branches. In one branch, the cat survives. In another, the cat does not. Both outcomes are real. Both persist, but they no longer interact. From the perspective of an observer inside one branch, only one outcome is visible. The other branch becomes inaccessible. This interpretation removes the need for sudden collapse. The mathematics remains continuous and elegant, yet it introduces an almost overwhelming vision of reality. Countless branches, an immense tree of possible histories, every quantum event generating divergence. Some physicists find this picture natural. Others find it extravagant. Then there are hidden variable theories. These propose that quantum randomness is only apparent. Beneath the wave function, there may be deeper variables determining outcomes precisely. We simply do not have access to them. In this view, the cat is always either alive or dead. We just cannot know which until we open the box. However, experiments testing Bell's inequalities suggest that any hidden variables must behave in ways that challenge classical notions of locality. Nature resists being simplified too easily. Objective collapse theories propose that superposition becomes unstable at larger scales. Beyond a certain complexity, the wave function spontaneously collapses. This would mean that microscopic systems can remain indefinite, but macroscopic systems naturally settle into definite states. Such theories attempt to modify the equations slightly. They preserve much of quantum mechanics while adding a mechanism for collapse. No interpretation has yet achieved universal agreement. Each carries strengths and difficulties. Each preserves the successful predictions of quantum mechanics. The cat remains suspended in interpretation. But perhaps the deeper lesson of Schrödinger's thought experiment is not about choosing the correct interpretation. Perhaps it is about recognizing the limits of intuition. Our everyday sense of reality evolved in a world of large objects, trees, rivers, stone, and soil. It did not evolve to grasp superposition. It did not evolve to picture wave functions spreading across possibility. Quantum mechanics asks us to loosen that grip, to accept that at the deepest level, certainty may not be fundamental. Possibility may come first. Definiteness may emerge only through interaction. The cat inside the box becomes a symbol of that boundary, a boundary between potential and actual, between mathematics and perception, between description and experience. When we open the box, we participate in the story. We do not merely observe, we interact. And through that interaction, one branch becomes our lived reality. Yet the underlying equations remain quiet and unchanged. They continue to describe a universe richer than appearance suggests. Let that richness rest softly in your awareness. Reality may not be as rigid as it seems. It may be layered, subtle, structured by probability beneath the surface of certainty. The sealed box becomes a meditation, a reminder that beneath the familiar world lies a deeper pattern, a pattern that does not rush to resolve itself, a pattern that allows overlapping possibilities to exist until interaction draws out one thread. Alive, dead, wave, particle, possibility, experience. There is no need to choose an interpretation tonight. You can simply allow the paradox to remain, a gentle question suspended in thought, like the cat itself, balanced between outcomes, resting within the quiet mathematics of the universe. Let us now allow the paradox to soften. We have followed the logic carefully. An atom in superposition, a detector entangled with that atom, a vial of poison linked to the detector, and a cat whose fate depends on a quantum event. Alive and dead within the mathematics, certain and uncertain at the same time. But now, instead of trying to solve the paradox, let us simply rest with it. The image of the sealed box can become something quieter. Not a dramatic scene, not a crisis, just a symbol of possibility. Inside the box, the system evolves gently. The wave function spreads across potential outcomes. Nothing rushes. Nothing forces a decision. Only probability unfolding according to precise, elegant rules. Perhaps this is not so different from the way thoughts exist before we grasp them. Before we focus on a single idea, the mind contains many possibilities, memories, images, questions. They overlap softly, not yet chosen, not yet fixed. When we attend to one thought, it becomes definite. It becomes the one we experience clearly. The others fade into the background. In that sense, awareness resembles measurement. Attention narrows possibility into experience. But until that moment, the field remains open. Schrödinger's cat invites us to imagine that openness at the level of reality itself. Before interaction, the world may not be fully decided. It may exist as a structured web of probabilities. Only when systems interact do definite outcomes emerge, and interaction is constant. Particles collide, photons scatter, energy exchanges. Through this vast network of interactions, the classical world takes shape. Tables feel solid, walls feel firm, cats appear either alive or not. Yet beneath that solidity lies the quiet layer of quantum possibility, a deeper pattern, a mathematical ocean beneath the visible surface. Imagine that ocean now, calm, dark, endless. Waves rising and falling, not chaotic, not violent, just patterned movement guided by precise laws. The cat in the box becomes a ripple in that ocean, a small fluctuation in the larger field of probability. And you, listening now, are also part of that field. Your body is composed of atoms following quantum rules, electrons orbiting in probability clouds, molecules vibrating gently, trillions of interactions occurring silently every second, and yet you feel stable, continuous, a whole. From overlapping probabilities emerges the experience of being. From microscopic uncertainty emerges macroscopic calm. The paradox of the cat does not threaten that calm. It enriches it. It reminds us that certainty may be an emergent property, a surface phenomenon. Beneath it, possibility continues to flow. When you lie quietly in the dark, your thoughts may feel uncertain, undefined, half-formed, like the cat suspended between outcomes. There is no need to force them into clarity. No need to open every box. You can allow them to remain soft, superposed, unresolved. Sleep itself is a gentle transition from definition to openness, from focused awareness to drifting imagery, from certainty to possibility. As you relax, the boundaries of thought become less sharp. Ideas overlap, memories blend. The mind enters its own subtle superposition, not fully awake, not yet dreaming, balanced between states. There is comfort in that balance. In quantum mechanics, superposition is not chaos. It is structured possibility. In the same way, the drifting mind is not disordered. It is simply less constrained, less measured, less fixed. The cat does not need to be resolved tonight. The box does not need to be opened. The wave function can remain uncollapsed. Possibility can remain possibility, and you can remain at rest within it. Imagine the sealed box resting quietly in a dark room, no one watching, no urgency. Inside, probability unfolds according to its own rhythm. Outside, the world continues calmly. Stars move across the sky. Air cools gently. Night deepens. The paradox becomes less a puzzle and more a quiet reminder. Reality may be deeper than appearance, and depth does not require tension. It requires stillness. Allow your breathing to slow. Inhale softly. Exhale gently, like waves settling after a distant disturbance. There is no need to decide between interpretations. No need to choose Copenhagen or many worlds. No need to determine whether collapse is real or apparent. The mathematics continues regardless. The universe continues regardless. And you can simply rest within it, alive, present, part of a reality that may be layered with possibility. The cat becomes a symbol of uncertainty. But uncertainty is not something to fear. It is the openness from which all outcomes arise. Let that openness become spacious. Let it become calm. Let it become sleep. Now let everything become even quieter. The box can remain closed. The question does not need an answer tonight. The atom can remain undecided. The cat can remain suspended in possibility. And you can remain here, resting gently between thoughts. Quantum mechanics teaches us that reality may not be fixed until interaction draws out a single thread. But there is no need to draw that thread now. You can allow your awareness to soften, to loosen, to drift without measurement. Imagine the sealed box fading into darkness, not alarming, not dramatic, just slowly dissolving into the quiet background of the night. The paradox becomes lighter, less a puzzle to solve, more a symbol of openness. Possibility does not demand resolution. It simply exists. In the same way, your thoughts do not demand conclusions. They can remain half-formed. They can remain undefined, like waves that have not yet reached the shore. Your breathing is steady. Your body is supported. Nothing needs to collapse into certainty. Nothing needs to be chosen. Alive, dead, wave, particle. These are only words describing deeper patterns, and those patterns continue calmly, whether we observe them or not. Let the ideas fade now. Let the mathematics soften into silence. Let the image of the cat drift away, like a distant star disappearing at dawn. You do not need to open the box. You do not need to look inside. You can simply rest, drifting gently between possibility and dream, into deeper quiet, into steady calm, into sleep